ask your question. Okay. Yes. So this is about optimal network structures and where we can find them. So I think from a network science perspective, this is about optimal subgraph structures. And from a network science perspective, this started around 20 years ago when people started investigating really large data sets. So for example, of the internet, but also many other data sets, such as this very beautiful network, which is a network of the interactions between proteins. So nodes in these networks are proteins, and edges represent that one protein can interact with the other protein. Now, of course, this is a very beautiful network, and to me, of course, it just looks like any other network you can think of. But then when some people start counting very small patterns, so small subgraphs in these types of data sets, they found very interesting patterns in them. So what they found was that these types of protein-protein interaction networks, this particular structure appeared much more often than other types of subgraphs on 4 nodes. And then, of course, you can wonder, is this the case for maybe all possible network data sets that you see? But then people started investigating. So maybe in other data sets, we will also see this particular subgraph appearing very often. But it turned out that if you look at other types of networks, you will see very different types of subgraphs appearing more often than other subgraphs of the same size. So in the internet, for example, there's a lot of stars. And in networks of collaborations, you often see a lot of peaks. And often these types of subgraphs that appear very often are sort of correlated with the function of the network. So for example, in networks that encode the interactions between genes, or gene networks or protein networks, interaction networks, these two things, they represent some specific type of reaction that is necessary for the system to function well. Whereas, for example, in collaboration network, you can easily imagine that if you have 4 people that collaborate together, all these 4 people have a link between them. So this explains intuitively why a clique should appear more often than you would expect. So then in network science, there started to be this term of motive, which is a small subgraph that appears more often than what you would expect. But then, of course, from a probability perspective, you can then wonder, okay, but then what is actually the number that I would expect? So if I have a network on 1,000 nodes and I count 20 cliques, is that more than I would expect, or is that less than I would expect? So for motive counting, you usually try to count how often a graph occurs as a subgraph. You can choose what you want to do. So in some cases, if you, for example, are interested in counting squares, in some cases you also say, I also include complete graphs, for example. Then we call it subgraph counting. In some cases, if you are doing induced subgraph counting, that also means you care about the non-edges. So if I want to find a square, if I want to count squares in a big network, that means I count squares, but I don't count these diamonds or complete graphs of size 4. So throughout this talk, I think we're mostly going to do induced subgraph counting, but for the results, it doesn't matter so much which of the two you're doing. Now, so as we said, so from my perspective, I'm interested in, so how many subgraphs would you expect as a baseline for example, for network data? So that means that I'm interested in the question. So how often does how many times does some specific graph that you're interested in, so let's say a square, how often does it appear as an induced subgraph in a random graph? So if we know, for example, the distribution of the number of subgraphs in a random graph, we can use that as a benchmark for real data, for example. But it turns out that for many realistic random graph models, this question is rather difficult to answer because many probabilities of the edges being present or not being present involved turn out to be dependent. So, but it turns out that if you first answer a more difficult question, which is on which vertices can you usually see a subgraph, then the first question is also more easy to answer. So what do I mean with which vertices does the subgraph appear? Well, so suppose I'm again interested in this square, and I have some big network in which I want to count or find squares. Now suppose that I find a square somewhere in this big graph, then all these vertices are of course also part of the larger graph. So they also have a degree in the large graph. Of course, the degree of a vertex inside the square, that is 2. But each vertex also has a degree inside the big graph. And as I will show you today, for many random graph models, it turns out that these vertices, so suppose that I find a square somewhere in my network, then often the vertices of these squares have very particular degrees. So, but to get started, we will answer this question for one specific random graph model, which is the inhomogeneous random graph. So in the inhomogeneous random graph, you have n vertices, and each vertex you associate with a weight, and then you connect vertices with some specific connection probability, which is the product of their weights divided by the average weight times n, minimum with 1. So that basically means the higher the weight, the higher the connection probability. So high weight vertices tend to have higher degrees. And in fact, if you choose the connection probabilities in this way, you can also say that you can also prove that the degree of a vertex will actually be rather close to its weight. So throughout the rest of this talk, I may interchange weights for degrees, and for the purpose of this talk, it also doesn't really matter whether you're talking about weights or about degrees. But this model is very interesting because for this model, you can now input any kinds of weights that you want, or any kinds of degrees that you want to achieve as input for the model, and then you can create this graph with on average at least the degrees that you want. But in this talk, what we will do is we will choose these weights randomly from a power law distribution. And in particular, a power law distribution which has infinite variance. And why? Well, this is because there's many papers that claim, also many papers that don't claim this, but there's at least there's a lot of evidence that in many real networks, the tails of the degree distributions are rather heavy. And one regime that is sometimes, that often also appears, is a regime where tau is between 2 and 3. So in this case, that would be infinite variance, but finite average degree. Now, let's suppose that we're interested in a very simple subgraph, which is a triangle. Now then, one very stupid way to count triangles in a network is to just have a sum, not over the vertices of the network, but the sum over all possible combination of 3 degrees. And then count how many triangles do I have between vertices of those degrees. So how many triangles do I have between one vertex of degree 4, one vertex of degree 6, and one vertex of degree 5? And if you then just sum over all possibilities that there are, you will in the end up with a triangle count in your entire network. And the interesting thing is that it turns out that this sum is actually dominated only by a very small part of the sum, of the summation. So you can basically leave away the summation and replace it by the maximum of these sums. So the number of triangles, we will see that it will be dominated by the number of triangles between very particular degrees. But then the question, of course, is how do we actually find those degrees? So, for the number of, let's say that we say, okay, we don't know what the degrees are, but let's say that they scale polynomially in a network size. So one vertex has degree n to the power alpha 1, one n to the power alpha 2, and one n to the power alpha 3. And then you can see that then you can write approximately at least the number of triangles of vertices on roughly those degrees. Well, at least in expectation, you could say, well, this is the number of vertices that are there in my graph with those degrees times the probability that they form a triangle. And you can actually show that this concentrates quite nicely, so that indeed the number of triangles with those degrees, you can actually just write as the number of vertices times how often they form a triangle. And the nice thing is that in this model, now that we know what the degrees are, we can easily write this out because, well, the number of vertices with specific degrees, well, we sample the degrees or weights uniformly from a parallel. So we can just say that this is actually equal to the first term. And then given that we know the weights, then the edges are again present independently. So then to form a triangle, we just need 3 edges to be present, which happens with these 3 probabilities. Now, and here we already see that there's some sort of trade-off going on between 2 effects, because on the one hand, high degree vertices are rare. And so because this term is negative, that means high degree vertices are rare. So this will decrease in all these alphas. On the other hand, high degree vertices, of course, have many connections, so are likely to appear in many triangles. So this term will actually increase in all these alphas, which says so on the one hand, it's not so good to include high degree vertices in your triangle because there are just not many of them. On the other hand, it's beneficial because they actually form more connections. So this now, if you can just write this as some exponent in n, and if you then optimize the exponent, you will find out that the optimizer over this alpha is given by all alphas equal 1/2. And remember that we were choosing the degrees as n to the power alpha, so that would be square root n degrees. And this is what we can actually prove, is that if you find, and what we can then prove is that if you find a triangle somewhere in your inhomogeneous random graph, with high probability, this triangle will have only vertices that have degrees roughly equal to square root n. Now, so the triangles was just one illustration of how this method works, but you can actually do this for all subgraphs you will be interested in. So now, suppose I'm not interested in a triangle, but I'm interested in some general subgraph H. I can again say, so if H has k vertices, then I say, well, all of them have some specific degree. And how likely am I to find my subgraph H on vertices on those degrees? How many of them are on those degrees? And again, then we just count how many vertices are there with specific degrees. And how likely, suppose that I have a set of those degrees, how likely is it that I see this specific subgraph H that I want? Now, now we can just write the exact same equation as before. So we found here, so how likely am I to sample vertices with those of orders of magnitudes weights from a parallel distribution times how likely am I to actually connect the edges that I need in my subgraph H. So suppose that I know the degrees, how likely is it that the edges that I need are there? And also, if we have an induced subgraph, how likely is it that the edges I don't want to be present in the subgraph to also not be there in the big subgraph? And this we can just write out in terms of the connection probability. And as you can see, it's not a very beautiful equation in all these alphas, but still for any subgraph that you give me, it's not that I mean, you can optimize this. So for example, here I showed 2 examples. So for example, we saw the triangle before, but it turns out that for actually all cliques of larger sizes, it will also be optimized on all these alphas equal 1/2. So cliques are with high probability found on vertices of degree square root n. But now suppose that I'm interested in this subgraph, I don't know what this name should be, but this subgraph with several triangles. Then it turns out that you will find it on very different locations in a graph. So then the optimal alphas are here, 1 divided by tau minus 1. And because tau is between 2 and 3, 1 divided by tau minus 1 is larger. So this is really a very high degree vertex. In fact, these, you could say, are the highest degree vertices that are present in your graph. Because if you sample from a parallel distribution with high probability, there will not be a degree higher than this. So you have 2 of those. And then 3 other vertices that have this weird exponent. So alpha equal to this quantity. And this, you can show that this is actually lower than a half. So you will have 3 rather low degree vertices and 2 extremely high degree vertices. Now, this is all nice, but of course, you can wonder, if I draw 10 more subgraphs, how many of these different orders of magnitude will I see? So now we already see, so a half, 1 divided by tau minus 1, this weird thing. But of course, I can draw many more subgraphs, and maybe all of them are found on different locations. But that turns out not to be the case. In fact, if there is a unique solution to this specific equation, it turns out that there's only 4 possible orders of magnitude on which you will see these the optimal subgraphs in your big graph. And most of them we've actually already seen. So we had these hubs, these very high degree vertices. So the only one we hadn't seen before is this theta of, so alpha equals 0. So that means n to the power 0, so constant degree. And that only appears actually if in the subgraph itself, the degree equals 1. And then there's also these other 2 magnitudes, so some middle degrees and some lower degree vertices as well. And then the nice thing is that if we can indeed prove that the optimizer to this optimization problem can only be given by 4 different orders of magnitude, and actually for one, we also already know that this will be the optimizer if and only if the degree of a vertex equals 1, which is easy to check. Then this actually makes it possible to rewrite this equation in a much more simple way, where we just say, okay, suppose we have some subgraph H, then we know we actually just have to partition it into 3 different groups. So the square root n degrees, these hubs, and these lower degree vertices, and then see which of these 3 partitions gives the highest contribution to this optimization problem. So I will not show you how to rewrite this optimization problem in this setting, but it turns out that then the optimization problem actually becomes very, very simple. And then this optimization problem tells you where you can find any given subgraph. So to be a little bit more precise, so suppose that this optimization problem has a unique solution. So there's a unique partition into these 3 different degree classes that optimizes this equation. Then we can say that the number of subgraphs, so that the number of subgraphs with the degrees in these correct ranges, so in the optimal ranges that we have, so in the ranges epsilon 1 divided by epsilon times n to the power alpha, where these alphas are the optimal alphas from these partitions. And if you divide it by all the subgraph counts, so also the ones with degrees that are not in the best intervals, this will converge in probability to 1. So really with high probability, all subgraphs turn out, so asymptotically, all subgraphs turn out as supposedly the subgraphs are dominated by the ones with the degrees in the right orders of magnitude. Now, the nice thing about this equation is also that it's very easy to now just draw a lot of pictures to see what's going on. So now here, these are all subgraphs on 4 vertices. And here I color coded it based on where you will find them in such very large graphs. So as we already saw, so cliques will always be found on square root n degree vertices, as do cycles apparently. But some subgraphs, for example, have a hub and a few lower degree vertices. And there's also, in this case, 2 subgraphs where our optimization problem doesn't give a unique solution. So they appear on a wider range of subgraphs. Actually, I think if this optimizer is not unique, usually it just means that you just add a logarithmic term or maybe a few more to the outcome that this optimizer would give, but that I will leave out of the discussion for now. And you can do the same thing for all subgraphs on size 5. Here you again can see, so some subgraphs are always formed on the square root n degrees, whereas others, especially the ones that are a bit less dense, you will usually find them with a few hubs and a few lower degree vertices. And you also really see that this is true, that vertices of degree 1 in the subgraph always have very low degree in the big. So here you can also really see that there's a very interesting trade-off also, again, between having hubs or not having hubs. So because for the dense graphs, it seems that including very high degree vertices is not so beneficial, but for sparse graphs, you see these hubs, so these dark colored vertices appearing more often. And this is again due to the trade-off that is given by this parallel degree distribution. Because on the one hand, it's good to, well, on the one hand, you want to include as many low degree vertices as possible. Because under a parallel degree distribution, you will have many low degree vertices, but only a few higher degree degrees vertices. But of course, if you only have low degree vertices, they are quite likely to not form the subgraph that you want. So in that case, if you can have many low degree vertices at the cost of maybe having one hub that connects, that is still relatively likely to connect to them, this can be beneficial in such a sparse case. But in a more dense case, having a few low degree vertices and maybe one hub to connect them doesn't make any sense, because then the lower degree vertices would also need to connect. So this really shows that you can find subgraphs at very different different types of locations, and that depends a bit on the shape of the subgraph. But what I think what is also very interesting to me is that basically all subgraph counts of all finite subgraphs all subgraphs of finite size are only located in very, very small portions of the graph, because you actually only need to count subgraphs between vertices of these 4 orders of magnitude, and you can delete the rest of your graph basically, and then still have an accurate subgraph count for all finite subgraphs. Okay, with maybe some extra logarithmic factors then for such ones, but even then, so there's actually, if you look at subgraphs, there's only a very small proportion of the graph that actually matters. Now, this is, so this was an illustration of this specific method where we applied it on models that where vertices have weights, and high weights means high probability connect. But these models are not extremely realistic. So one reason why they are not so realistic is that in these types of models that I just showed, these inhomogeneous random graphs, it's quite unlikely that you will find a triangle, because all connections are independent. So the probability that 3 independent unlikely connections happen is even more unlikely. Whereas in most real data, for example, such as social networks or other types of networks, is quite, you usually see many triangles, because often two friends of a friend are also friends themselves. So for this reason, we also started looking at a much more realistic network model, but which is still a little bit like the model we had before. So in this model, we say, okay, suppose that we again give every vertex a weight, which is again uniformly drawn from a parallel distribution. But now we also give every vertex a uniform position, let's say on a torus, a d-dimensional torus. And now, given these positions and weights, we connect the vertices with the product of the weights again, divided by the average weight times n, but now also times the distance to the power d. So that means, so if you're very close by, you're much more likely to connect than when you're far away. So in these models, there are essentially two ways to form connections. So on the one hand, what you can do is have a very high weight to get this connection probability as high as possible. So then you're like Taylor Swift. Or you can also just be very close to someone, so that maybe your family members. And because you're so close, you're also still very likely to connect. So here there's an illustration of the model. So here you see some low degree vertices that are connecting, but also some hubs that also connect to some further away vertices. And so this model again has a parallel degree distribution because we chose the weights as a parallel. But another desirable property of this model is that now actually you have a lot of triangles, because if two vertices connect, then they are likely to be close in the underlying torus. So because the distance then between two connections, the distance between two of your friends is by the triangle inequality cannot be too large. So they're quite likely to connect as well. So these are very nice, nice properties, but from analyzing a subgraph perspective, these properties also make it a bit difficult, because before we could just say, well, suppose that we know the weights, we can just multiply all the connection probabilities to get the probability that, for example, a triangle appears. Here we can not do that, because suppose that that these two edges appear, the probability that this one appears is not independent anymore of the previous connections because of the underlying geometry. Because we know that two connections are there, they're likely to be close, so this other edge is also more likely to be present. So to still apply our method, we have to make the problem a bit more complex. So remember, what we were trying to go for is try to find out on which vertices in my graph am I most likely to find this square, for example. I mean, before we said on which vertices means on which degrees will I find it. Now, in this case, in this model, we actually have more parameters. So in this case, what it means, where am I most likely to find a square? That means, well, what are the degrees involved in making this square? But also, what are the distances between edges in a square? So for example, do I have one edge which is has a very small distance, one with a longer one, and here's some others, or are they all very short? Or what are the distances between vertices in a subgraph that I see? So how to make it more precise? So remember, before what we wanted to find is we wanted to show that if I want to count specific subgraphs H, I want to count how many of them appear on vertices, how many subgraphs appear between vertices of specific degrees. Now, in this case, what I also want to have is I want to have vertices. So I want to show that there's not only optimal degrees for the vertices in the subgraph, but also optimal distances So that I'm almost every time I find a subgraph, I find them between vertices of specific distances. So these would be the optimal distances. So again, we say we let the degree scale as n to the power alpha. But now he also says now I let the distances between vertices I and j scale as n to the power beta ij. So because we're on a 0, 1 torus, this beta will be negative because the maximum distance is a half on the torus. And in the end, the goal is to find what are the optimal ways of these to finding these optimal alphas and these betas. Now, the problematic thing here is that here I only draw these things for the edges. So for example, if this would be vertex 1, I want to have that this distance scales as n to the power beta 1, 3. This distance scales as n to the power beta 3, 4, and so on. Now, the difficulty with this optimization thing is that not previously for the degrees, you can just have any possible combination of 6 degrees, and they can form a subgraph of 6 vertices. With distances, of course, this is not the case. Because, for example, what you cannot have is this, where this distance is very long. This is n to the power 0, so let's say distance 1. And these distances are all very small. And why can this not happen? Because we are on a torus, so we should satisfy the triangle inequality, and then we would say that the distance between this one to this one is 1. But actually here, let's say we're usually interested in a large n limit, but I can also get from this vertex to this vertex in four very extremely small steps, which will be definitely smaller than 1. So in this case, the triangle inequality is violated. The distance from 1 to 4 is in this case larger than the distance of a much larger path from 1 to 4. So this is not possible, and this we want to exclude. And so because we scale the betas are these, because we had that the distance scale at n to the power beta ij, you can show that then the triangle inequality actually says that if I have 3 vertices, it cannot be that 2 here have a shorter path than the other one. And then, so here I will also skip a bit through this because the writing this is a bit more painful, but what you can then show is that if you have such a geometric model, you can actually transfer finding the subgraph counts to solving this. You can rewrite it as a mixed integer linear program. This is a other reformulation where you optimize over these alphas and these betas. So here you could see the contribution of that you don't want to add hubs because there's only few of them. This is some term which was a bit, this is how likely am I to find, suppose I want to have vertices at particular interdistances. How likely is it that I can even find such a combination of distances? And then here is a term that then tells you, so how likely are these vertices of the right degrees and distances to form my subgraph? And then subject to the triangle inequality. So here I made then again some pictures of what this does, because if you optimize this, this means that you will have found, again, that you can show that if I find a copy of this subgraph, if the solution to this problem is unique, and I find a copy of this subgraph somewhere in my big graph, if with high probability it satisfies these optimal alphas and betas. So here I just also made some pictures to see that here it's actually, the picture becomes even more interesting because you see some vertices, some subgraphs are often formed between vertices of very low degree with small distances. I didn't quantify it here because it becomes a bit too much. Otherwise, with both the distances and the vertex weights. whereas others appear more, for example, with vertices of higher degree and also further away ones. But interestingly, here there's a very intricate relation with how strong the power law is. So in this case, the power law exponent is close to 3, so not a very strong power law. And what you could say here is that these specific subgraphs, they, before in the inhomogeneous random graph where we didn't have the geometry, we had that these subgraphs were appearing on vertices with degree roughly square root n. Now we added the geometry, we see that now they're actually formed by geometry. They're formed by very low degree vertices that are extremely close by each other. So intuitively, you could say that these are geometric subgraphs. They are formed due to the small distances of the geometry. If you go to so a much lower power law, interestingly, subgraphs are formed in completely different ways. So all these geometric subgraphs that we had before, for example, are now again formed by square root n. So this is square root n degree vertices that are extremely far away from each other. So if the power law is very strong, it basically means that the subgraphs don't really see the geometry anymore, because subgraphs are usually formed between vertices that are as far away as possible. And what we can actually show is that there's a phase transition depending on the size of your for cliques. We can show that there's a phase transition in the size of your clique and tall, so that when you have small cliques scale linearly and they are formed between close by vertices, so the geometric case. When k is larger, then cliques have a different scaling, but also then we can show that they appear exactly in the same way as in the inhomogeneous random graph. And so here I just plotted this phase transition. But what is most interesting to me here is that at some point, which is here, even triangles behave the same as if they were in a non-geometric model. So here we say that so what does this mean? So here we say, so in this case, the red phase is the geometric cliques, and these ones are non-geometric. And so the phase transition was in tau and k, but here it says, well, but now suppose that you have a tau very small, close to 2, then it means that even triangles do not behave as if they see the geometry. They just behave as in an inhomogeneous random graph. Above this, of course, sometimes triangles behave as if they're geometric, but not for cliques or other higher cliques. But there is a phase of this model where the power law basically dominates everything. So the power law forms the triangles, the 4 cliques, the 5 cliques, and you cannot really assess geometry from looking at triangles. And this is very contrary to the common idea that, well, if you add a geometric space, you have a triangle inequality, so you should add, that means that it should add many triangles. But in this case, that is actually not true, because the power law basically dominates everything. Yes, that is here. But it turns out that still, so that means that if you just count triangles, you can't really distinguish between geometric and non-geometric graphs. But it turns out that if you want, suppose you are given some graph and you want to know, was this graph generated by a geometric or by a non-geometric model? You can actually design a different statistic that still does the job. So as we see here, so if you so here, if we just count triangles, then the geometric and the non-geometric model behave very similar. Of course, there's a difference in the height of the lines, but that depends very much on the parameters of the model, which are usually not possible to detect from a given network sample. And here there's another common use network statistic that also doesn't do so well. But interestingly, if you just weigh the triangles a bit differently, so then you can very easily distinguish between these, between these geometric and non-geometric models. Now, finally, I will just very briefly show that this model is not only applicable, this method of optimizing over subgraphs is not only applicable to these models that I showed you before, but also to a different class of network models, preferential attachment models. So this is actually a class of models where the network starts growing. So you start with one vertex, and then vertices start appearing. At each time a new vertex appears, and then it attaches to a vertex I with probability proportional to the degree of vertex I. So that is like the rich get richer effect. So the more, the higher your degree, the more likely a new vertex is also to attach to you. And there is some parameter delta that then tunes the parallel exponent that this model will turn out to have in the end. But it turns out that now, of course, vertices don't have weights because the graph is just growing. But it turns out that if you then maybe don't consider the weight of a vertex, but the age of a vertex, so was this vertex vertex number 1, or was it maybe the last vertex to end? And then if you have their ages here, then you can still write the probability that you form a subgraph as well, still some product of some of these, well, not weights, but ages. And this is still a product over the edges. And so then here you can you do the exact same method, because you can just compute how many vertices are there with a specific order of magnitude of age. And given this equation, you can then also just say, how likely are they to form a subgraph? And then here you can just do the exact same method for a preferential attachment model as well, and then see what type of subgraphs. So where in a preferential attachment model am I most likely to see a specific subgraph? So interesting. So in a preferential attachment model, these subgraphs are also directed, because a new vertex appears and it attaches to a previous vertex. So usually we say that this connection is directed. And then you can also see that different types of directed subgraphs appear on different types of vertices. So here I translated the ages back to degrees. So some are, for example, often found on vertices with very small degrees. And this one apparently depends on tau, whether degree is small or large. And some are formed on many high degree vertices, but one small degree vertex. And for some, we know that, for example, one vertex has small degree, one vertex is high degree, and these two can have any degree. And that then often just adds some logarithmic factors to how many of them you will see. In any case, so the main conclusion is that in many different types of networks, you will see that if you count subgraphs, they only appear at very specific orders of magnitude of degrees. And yeah, so for most of the models that you can think of, I think they will only appear on very few of those. And the other interesting thing is that this exact same method is not only able to count subgraphs or to find where they are, but also if you look at other degree-based statistics such as clustering coefficients, but also this new statistic that we designed to assess whether there is geometry or not. Thank you.
All right, thanks, Clara.